webinar series. Today, we will have the pleasure of discussing current trends and future strategies for both electric and hybrid vehicles. My name is Andres Bryan, and I'm a senior biomedical engineering student here at the University of Houston, and I will be the moderator for today's event. Before we begin with the event for today, I want to take a minute to thank our partner Evolve Houston, as we are very fortunate to have them working with us to help spread awareness about electric vehicles. I'd also like to take a moment to remind everyone of our next webinar on February 12th, where Dr. Krishnamurthy will address electrification of rail and sea transportation. To learn more about the electric vehicle webinar series and our past webinars, please visit the Energy EV webpage using the link above. Moving forward, we will have the Q&A session at the end of the presentation, so please hold on to your questions until the end. That being said, we will be utilizing the chat function throughout the presentation. So if you have a question, go ahead and send it in, and we will answer the questions at the end of the presentation in the order they are received. Without further ado, I would like to introduce Dr. Kaushik Rajashekara. Dr. Rajashekara joined Delphi Division of General Motors Corporation in Indianapolis, Indiana as a staff project engineer. During his time there, he held various lead technical and managerial positions. He was a technical fellow and the chief scientist for developing electric machines, controllers, and power electronic systems for electric, hybrid, and fuel cell vehicle systems. In 2006, he joined Rolls-Royce Corporation as a chief technologist for more electric architectures and power conversion control technologies for aero, marine, defense, and energy applications. In August of 2012, he joined the University of Texas at Dallas as a distinguished professor of engineering. Since September of 2016, he is a distinguished professor of engineering at the University of Houston. He has worked in both automotive and aerospace electrification systems, and Professor Rajashekara was elected as a member of the National Academy of Engineering in 2012 for contributions to electric power conversion systems and transportation. In the last 10 years, a large increase of electric vehicles around the world have significantly increased the perception of their viability and usefulness in reducing emissions. In addition, more than 400,000 plug-in electric vehicles are on the road today, as well as fuel cell vehicles that are also being gradually introduced into the market. In this seminar, the recent advancements in electric and hybrid vehicles, current trends, and future strategies will be presented. This presentation will also discuss the operation and architectures of electric vehicles and hybrid vehicles, along with challenges related to motors, power electronics, and batteries.
Today, I'm going to present on electric and hybrid vehicles, current trends, and future strategies. So we will discuss about a brief history of electric vehicles and electric vehicle architectures, and we will also look at the difference between the electric vehicles and the hybrid vehicles, some aspects about the electric vehicle charging, and we will also discuss the challenges and the future. So the electric vehicle was first invented in 1834 by Thomas Davenport. That is based on the non-rechargeable batteries. And it was giving about 19 miles per hour. That was, of course, at that time it was fine, but generally it is very slow. Then it became popular or more popular after 1859 when lead acid storage battery was developed for the electric vehicles so that they could recharge the batteries. Battery powered carriage was developed in 1874. As you can see from the history, there were more electric vehicles sold in the 1890s than the gas powered vehicles. The companies like Volkswagen, which was part of General Motors, as today Baker, they started as electric vehicle companies. So in 1900, 38% of the electric vehicles were sold, or vehicles sold were 38% electric and 22% gasoline powered. So more electric vehicles were sold than the gasoline powered vehicles. After 1920s, gradually the use of electric vehicles disappeared or declined, and more gasoline powered vehicles were used. So these are some of the early electric vehicles. 1914 Detroit electric car, and these are the first electric car by Thomas Davenport. So why did the electric vehicles disappear after 1920s? Because they were expensive. The gasoline-powered car, that is the Ford Model T at the time, was selling at $260. That is 1925. And the gasoline vehicles became less and less expensive. And 1909, $850. But in 1925, it became $260. But the electric vehicles are quite expensive. And the other one is the rural areas had very limited access to electricity to recharge the batteries. Whereas you can fill in your gas tank at any place. And the next item is the emissions. So why did the electric vehicles again came into operation? Why it is resurged? That is because of the resurgence of EVs in 1960s were because mainly due to the emissions. So Clean Air Act was enacted in 1970, and also Congress introduced the bills recommending the use of EVs as a means of reducing air pollution. So from 1920s to 1960s, there were no electric vehicles for commercial purpose. There were, of course, always some demonstration vehicles, but not commercially available. So there was more emphasis on reducing the pollutions after 1970s. For example, in 2019, the global emissions were 34 gigatons and USA emitted 4.9 gigatons. So the transportation contribution is the highest for all the emissions. Transportation contributed about 28% of the emissions when compared to the electricity 27% and industry 22%. Okay. This was 2019. Or 2020, it may be slightly less because of the COVID. So the electric vehicles became more and more popular gradually, but not were commercially available till 1990s. I will come to that explanation. Before that, I want to tell you what is an electric vehicle. An electric vehicle is just like any other vehicle. Instead of the internal combustion engine, the propulsion is provided by the electric motor. The electric motor gets its power from the battery, and generally all the electric motors or the motors that are being used by all the automotive manufacturers are AC motors. So, but the battery power is DC, so DC has to be converted into AC. So there is an inverter. Inverter converts DC to AC of variable frequency and variable voltage. That is what it requires for the motor to run at different speeds and to give different power. Okay. So the battery, we have an inverter which converts DC to AC and the motor which provides the propulsion power. And there is a converter. This converter is used for boosting the battery voltage to a higher voltage. The recent trend is to use the higher voltage of the inverter input so that you can reduce the current requirement, and so the cable sizes can be lower. But the battery is at a lower voltage, so it has to be boosted. So this acts as a boost converter to the boost to the required voltage for the inverter. And there is one more converter. This is for bringing down the battery voltage, say from 300 to 400 volts to 12 volts DC or 14 volts battery to charge the 14 volts batteries. So which provides the power for all the accessory loads such as lighting and power steering and the electric air conditioning, if it has, of course it is a, or air conditioning can be run from directly the battery. Generally, almost all the electric vehicles, air conditioning unit is run from this battery voltage directly rather than going through this. But in regular internal combustion engines, the 12 volts battery can run the electrical air conditioning if it is used. They are mostly belt-driven systems. And the charger is used for charging the batteries. This is an onboard charger. So whenever you stop the vehicle at the workplace or at home, so you can connect this charger to the outlet and then charge the batteries. So this converter, which I mentioned as a boost converter, it is not used in all the electric vehicles. For example, GM vehicles, they don't use that. Even Tesla vehicle doesn't use that. But Toyota Prius uses it. And we will talk about that a little later. So it is not required, but this converter is required in all the vehicles. Okay. So coming back to the commercial aspect of the electric vehicles. So GM Impact was, I would say, a prototype version of the GM EV1. So GM Impact was the technology developed for GM Impact was used for GM EV1. The GM EV1 was the first commercially available electric vehicle. That was from 1996 to 1999. So the Impact prototype used induction motors. There were 2 induction motors at the front wheel, so hence there were 2 inverters. And at the time, we were using MOSFETs. This is my first project when I joined General Motors to work on this system. We worked with AeroVironment for development of this vehicle. So at that time, as I said, there were no IGBTs, so MOSFETs. So 24 MOSFETs were connected in parallel, and there were 2 inverters because there were 2 motors. And the battery was a lead acid battery, and the battery itself was weighing about 395 kilograms, more than 1/3 the weight of the total vehicle. The range of this vehicle was, even though it says here 120 miles, I would say about 80 miles in actual cases. And you could recharge in 2 hours. So this is the GM EV1 which was developed. This was on lease from General Motors from 1996 to 1999. This was a very good electric vehicle and performance was good. The only thing is the range was not as high as that was expected. It was again about 80 to 90 miles. And it was expensive, this vehicle. And many people could not buy that or lease it. And everything was electric here, electrically heated windshield. And the heating was electric. And braking was electric. Everything was more or less electric. Yeah. So 1997, the Toyota Prius came. So there was a hybrid vehicle which was giving a much higher range and also miles per gallon, equivalent miles per gallon than the electric vehicle of GM EV1, electric vehicle EV1. And also it was less expensive. So people didn't have to worry about the range of the vehicle. It is like a regular any other gasoline vehicle, and whenever you need to fill up the gasoline, you can go to a gas station and fill it up. So gradually it declined after 1997, the use of electric vehicles. till Tesla came out with the Tesla Roadster 2008. It was an expensive vehicle. It is a pure electric vehicle, but it had a very good performance. It was like a luxury electric vehicle. And they were the first to use the lithium ion batteries. At the time, there were no modules were available. So they took the laptop batteries and then connected them in series and parallel to achieve the required voltage and required kilowatt hours. And the cost of this was about $100,000. And several people bought it because there was a very nice car. And it was like a status symbol at the time for having this Tesla Roadster. Then Model S came, that is again Tesla Model S in 2012. It has a lot of features, and also the range was higher, 230 miles range. And also it has a 10 kilowatt capable battery charger, 10 kilowatt capable onboard charger with the following input compatibility. So you can charge either at 120 volts or 240 volts. And this electric vehicle became very famous. A lot of people bought it, even though it was expensive, because the range anxiety was less in this case because it was 230 miles. That was enough for most people. And also, if with 85 kilowatt hour battery, you could go up to 300 miles. Next one is, so now there are a lot of electric vehicles. We have a Nissan Leaf, Tesla Model S, Kia Soul, and every automotive manufacturer is now more or less producing electric vehicles. Okay. For example, Nissan Leaf is another famous electric vehicle. It has a range of 107 miles. It is less expensive than Tesla vehicles. And it has a battery energy of 30 kilowatt hours. Now, almost all the, I would say all the electric vehicle manufacturers, they use lithium ion batteries. Okay. This is the range again, 107 miles. Now let us look at hybrid vehicles. So what is the difference between an electric vehicle and a hybrid vehicle? In a hybrid vehicle, you have an internal combustion engine and also an electric motor. So depending on series hybrid or parallel hybrid, the internal combustion engine plays a different role. So for example, a series hybrid vehicle, here you see that, it looks exactly like a propulsion aspect similar to an electric vehicle, pure electric vehicle. So pure electric vehicle, battery, inverter and motor, and here also battery, inverter and motor. So 100% of the propulsion is provided by the electric motor. But there is an engine and a generator. Engine drives the generator, and whenever the battery state of charge falls below a certain level, the engine is turned on and it drives the generator and charges the battery. So battery state of charge can be maintained at a certain level by this series hybrid vehicle configuration. In parallel hybrid vehicle, there is an internal combustion and also electric motor. You can see that both of them can provide the propulsion at the same time. So the engine can also drive the vehicle, and the motor power can be combined with the engine power and also provides the propulsion power. So both are combined together. That's why it is called parallel hybrid. And also there is a plug-in hybrid vehicle. A plug-in hybrid vehicle is slightly different from the hybrid vehicle, whereas plug-in hybrid vehicle can be recharged at home during night time or at workplace. Otherwise, it is similar to the other hybrid electric vehicle. You can see here both are similar, except the battery can be charged at night or whenever it is parked. Also, the size of the battery is bigger than the regular hybrid vehicles. In hybrid vehicles, the battery is charged while the vehicle is running. In plug-in hybrid vehicle, the battery can be charged when the vehicle is running and also when it is parked. So this is the electric vehicle. So there is slight similarity between the electric vehicle and PHEV, and also a lot of similarity between the HEV and PHEV. So there are other types of hybrid vehicles also. They are called micro hybrid, mild hybrid, full hybrid. They are all parallel configurations. In series hybrid vehicle, there is another type called the range extender in addition to the full series hybrid vehicle. In a parallel hybrid vehicle, for example, you see this diagram. As it goes from micro hybrid to full hybrid, the size of the engine decreases, but the size of the electric motor increases, and the size of the battery also increases. If the size of the electric motor is less, the battery size is also less. A micro hybrid is almost equivalent to presently being used internal combustion engine. Only the difference is the alternator in the IC engine based vehicle is replaced by starter generator system. So you make the alternator not only as a generator but also as a motor. So that can be used for starting the engine. So when the vehicle is stopped at the signal lights, you press on the acceleration pedal, then the engine starts and you can move forward. So when you stop the engine at the signal lights and also stop the engine when it is decelerating, then you can save some fuel and also reduce the emissions. In the mild hybrid, it supports the engine during acceleration and also if you want to pass another vehicle and hill climbing, and also during regeneration, the electric motor assists. So all these functions can be achieved in the mild hybrid vehicle. In a full hybrid vehicle, it is like Toyota Prius. You can also operate as a pure electric vehicle, and all the other functions of the mild hybrid and micro hybrid can be achieved. In a series hybrid vehicle, if the engine is small and the generator is also small, then it is a range extender vehicle. So whenever the battery state of charge is low, you can turn on the engine and it drives the generator and charges the battery. And also it is possible for the engine driving the generator to power the electric motor directly in addition to the power coming from the battery. So the power is shared between the generator and the battery. Then it is a full series hybrid vehicle. It is possible that we can replace the engine and the generator by a fuel cell vehicle, then it becomes a fuel cell. See, this is a fuel cell vehicle. So if you look at the degree of hybridization, micro hybrid does only start-stop function. Mild hybrid can do, in addition to start-stop, regenerative braking and also assist the internal combustion engine during acceleration and passing a vehicle. A full hybrid, it can be used for driving as a pure electric vehicle also. And a plug-in hybrid vehicle, it can be recharged from the wall outlet when it is parked. Micro hybrid can give 5 to 10% in the fuel economy, but the motor needs are 3 kilowatt to 5 kilowatt. Mild hybrid reduces the fuel consumption by about 7 to 15%. The motor power is 10 to 15 kilowatt. Full hybrid fuel economy is more than 30%, but the electric motor is more than 20 kilowatt. And plug-in hybrid, which can be driven as a pure electric vehicle for a certain time. So it can provide fuel economy of greater than 50% and also lower emission reduction. And the power levels are also greater than 20 kilowatt on an average. And also it needs a bigger battery when compared to the regular hybrid vehicle. So now briefly look at the micro and mild hybrids. As I said earlier, for the micro hybrid, you replace the alternator in the existing internal combustion engine vehicles by integrated starter generator. This is actually a belt-driven integrated starter generator system. So the generator is driven with a belt. So you take the generator and make it as a motor and a generator. So you need an inverter. So you have to add an inverter to make that electric machine work as a motor. Okay. Integrated starter generator or integrated starter alternator, it does not have a large starter alternator external to the powertrain. So it can transmit more power since it is not limited by the belt drive. The motor is mounted between the transmission and the engine. This is where the motor is mounted here. This is the integrated starter generator. So series hybrid vehicle, if you look at it, the power to the propulsion motor goes from the engine driving the generator, and there is a rectifier, and then to the motor controller, which has inverter, etc. Inverter, gate drives, controllers, everything, and the motor. And also the power is coming from the batteries. When the power required by the motor is not that high, the engine can charge the batteries, and also engine driving the generator can also provide the propulsion power. That is the series hybrid vehicle. So it needs two electric machines, a generator and an electric motor, of course, an engine and a rectifier, etc. So generator is usually sized for continuous power of the vehicle, and motor is sized for peak power of the vehicle. Parallel hybrid vehicle, the propulsion power is coming from the engine, and the propulsion power is also coming from the battery. So both are combined in the transmission. That is the parallel hybrid vehicle. So it is also possible that you can remove the clutch here or open the clutch, then it becomes a pure electric vehicle. So you can drive it as a pure electric vehicle also. The engine size is smaller when compared to the regular internal combustion engine vehicle here, because there is an electric motor that provides the propulsion power also. Then there is a series parallel combination of hybrid electric vehicles. So this is one path, and this is the series path here. So the Toyota Prius uses an architecture like this. So the power is combined from the engine and also from the power coming from the battery together and drives the wheels. And there is a generator here, and it charges the batteries. So this shows the complete architecture of the system. It is also possible that the electric motor drives the rear wheels, and the front wheels are driven by the internal combustion engine directly. So this is the Toyota hybrid system. Toyota uses this architecture in almost all their hybrid vehicles. So this is where the power from the engine, the power coming from the battery, they are all combined, and also the generator power are all combined into one system here. That is the planetary gear system, or a hybrid system, they call it. And the power is going to the wheels. Okay. So the Toyota Prius operates like this. When starting or moving under very low loads, you can see that it starts as the pulse and provides the propulsion power. The differential is here. Under normal driving, so where is the power coming from? The power is coming from the engine driving the generator. So the power is coming from here, and the engine, so it is coming directly from the engine. Engine also drives the generator and charges the battery. And depending on whether the power is needed by the motor or engine, it is possible that the power also can come from here. Or it is also possible that the power directly goes like this without even charging the batteries, depending on how much power that is required. On full throttle conditions, where maximum power is needed, then the power is coming from the internal combustion engine and the battery. Yeah. So all the power is going to the propulsion system. Yeah. Under normal or under deceleration or braking conditions, this motor acts as a generator and recharges the battery. So this is a plug-in hybrid vehicle. A plug-in hybrid vehicle, as I mentioned earlier, which can be charged whenever the vehicle is parked in the garage or at the workplace. And you can go certain miles as a pure electric vehicle. For example, Prius Prime, you can go about 28 miles. Then if you go for long distance, then battery start depleting. Then at that time, you can turn on the engine and it charges the battery. And then you can maintain the charge, the state of charge of the battery at a certain level by turning on and turning off the engine. This Chevy Volt plug-in hybrid vehicle, it is no longer available. It is discontinued. It was a most famous or very well-known plug-in hybrid vehicle. So it was giving miles, 106 miles per gallon equivalent. And it has a pure electric vehicle range of 53 miles. As long as you drive less than 53 miles per day, then you never have to charge the, you never have to fill in the gasoline. And 420 miles was the combined, the electric and with the gasoline, you could go 420 miles. It was using lithium-ion batteries. It is discontinued, not because of the problem with technology or anything, because it was slightly expensive, and also General Motors could not sell as many as they wanted to. Toyota Prius plug-in hybrid or Prius Prime is also available. It is a 2017 model as 25 miles. I think the recent one is 28 miles of electric vehicle range. And you can, this is a, where is the total? 62 miles, yeah, 640 miles you can go with full tank of gasoline, with fully charged battery. The recent one is 2020 Mitsubishi Outlander plug-in hybrid vehicle. It has a range of 310 miles. This is a bigger vehicle, and pure electric vehicle range is 22 miles. Toyota Mirai fuel cell is also available. So in addition to electric and hybrid vehicles, there are a few other companies are also making fuel cell vehicles like Toyota, Hyundai, and also Honda. They're all working on fuel cell vehicles. So this is 2021 Toyota Mirai fuel cell, but it is quite expensive. Range is 650 kilometers, and it has 5.6 kilograms of hydrogen. 1 gallon of gasoline. 1 gallon of gasoline has the same amount of energy as 1 kilogram of hydrogen. So one gallon of gasoline is burnt in the vehicle, it produces 19 pounds of carbon dioxide. Whereas 1 kilogram of hydrogen is burned, you don't produce any emissions. Lithium ion battery that is being used is 310 volts. It has a range of 400 and, this and this are same. So 404 miles. Now electric vehicle charging, there are two types of charging, conductive charging and inductive charging or wireless charging. Conductive charging is where you take the charger and connect it to the wall outlet, and then it is discharged. Inductive charging is, you can see here, you just drive the vehicle up to a certain point. There is a pad here, and then you stop there, it automatically charges. Okay. So that is the way inductive charging. You don't have to do anything. You don't have to get down and connect the plug to the wall outlet. So this is the structure of electric vehicle battery charging system. So this is the AC, there is a AC to DC converter, and then there is a DC to DC converter, and you charge the batteries. The trend these days is to use the bi-directional converters so that you can also use the vehicle battery to connect it to the grid. Then you have a bi-directional DC-DC converter, and then the power goes from battery to the grid, and when you charge the batteries, power goes from the grid to the batteries. And there are fast charging systems are available now. They have been available for some time, but still it is recent. Tesla has number of super fast charging stations, and there are 150 kilowatt charger by Siemens is available, and BYD, the Chinese company, has a new 1 kilowatt DC fast charger, and it has a UL certification also, that is the Underwriter Labs in the United States. This is the bi-directional onboard charger from the company Bell Power. Okay. So it can be connected to 240 volts AC or 400 volts AC three-phase system. And so you can have a bi-directional operation. Yeah. So this is the architecture for a wireless EV battery charging. There is a three-phase AC, and this is like a primary of the transformer. The secondary is here, it picks up, and then AC is rectified, and then there is a DC-DC converter, and it charges the batteries. So what are the challenges? So challenges for the electric vehicles or the electric motors. Right now, most of the, or almost all of the automotive manufacturers are using permanent magnet motors. But permanent magnet motors are expensive, and also at higher temperatures they may demagnetize, and also there is a fault tolerant problem, but still they are very high in efficiencies and also high power density. That's why all the automotive manufacturers, they are still using PM motors. But over a long run, it is possible that we may move to electric motors like synchronous reluctance motors where no permanent magnets, but you can add a slide permanent magnet motor to make it better. Okay. And induction motor was the one that was used in early electric vehicles. Power electronics, there are also some challenges, even though power electronics has advanced a lot. The packaging, the EMI aspects, and also we want to reduce the cooling system. That's why automotive companies are trying to work on silicon carbide and gallium nitride high temperature devices. They can operate theoretically up to 300 degrees Celsius. So then you don't have to have this much big inverters. You can reduce the size. So up to 160 size you can go by using the silicon carbide devices. And the latest tendency is to integrate the motor and the power electronics or the inverter together. So there are companies like Borg Warner, which has supplied a lot of electric drive systems to from many automotive companies. And also, this is another company, McLaren Applied Technologies. So they are putting the inverter and the motor together so that you connect only the battery, two inputs from the battery, and everything is done. So you don't see the inverter itself from outside. So everything is integrated. So this one is slightly different, but they're all integrated together. So I need to tell you something about the batteries because that is the most important one. As I mentioned earlier, all the automotive manufacturers now use lithium-ion batteries. Lithium-ion has 3 times the energy density and power density of the lead-acid batteries. And there are several types of lithium-ion batteries, but most commonly used ones are lithium-ion cobalt, lithium-ion manganese, and lithium-ion phosphate. So there is a tendency to go for different types of batteries because the lithium-ion batteries use liquid or polymer electrolyte, and that has led to some safety concerns. So using a solid-state battery, it makes it more safer. So they work in the same way as current batteries do, but the change in materials alters some battery attributes. So including the storage capacity, charging time, size, and safety. So they are lightweight, smaller, and higher capacity, and cheaper than current liquid-based lithium-ion batteries. Okay. So several companies are working on this type of technology. And another technology which is long-term, the lithium air batteries, that also being looked upon by few companies, that has a much higher energy density than any of the other batteries. So, but that will be a long time to go. So the electrical and electronic technical team roadmap provided by the Department of Energy, their target for the electric traction drive system by 2025 is $6 per kilowatt and power density of 33 kilowatt per liter. Right now, by 2020, it is only 4. So they want 88% volume reduction. The electric motor, the power density has to be increased or volume reduction has to be done 89%. Efficiency has to go to 98%, and power electronics cost has to be $2.7 per kilowatt. So a lot of challenges there, even for DC-DC converters. So what is the trend? So the future will be more on silicon carbide based vehicles because we went from MOSFET to IGBT. Now we are looking at silicon carbide MOSFET based vehicles. Then advanced high density packaging and operating at junction of 250 degrees Celsius. And the motors, as I mentioned earlier, the manufacturers were using induction motors. Then right now everybody is using PM motors. The future could be synchronous reluctance motors. And presently no standards for battery voltage. Everybody uses different voltages for the battery. I think there has to be some standard for these battery voltages. And regarding the battery itself, now it is lithium ion, but in future it could be solid state and in long term lithium air. And more it will be wireless charging. And also renewable energy will be used for charging. And all the vehicles are able to do V2G, G2V operation. So we can connect the battery of the electric vehicles to the grid and participate as a microgrid or provide the power. So that will help in reducing the number of new plants or power plants built. And the future will be all driverless, autonomous and connected vehicles. There is a lot of work going on in that area. And then 3D printing, packaging and minimization is the trend. new materials and processes. And a lot of work is going on flying cars and vertical takeoff and landing vehicles, like air taxis and others. Anyway, we don't have time to talk about that. So that will be the future in next several years. Okay, thank you.
Thank you for the informative presentation, Dr. Rajashekara.
Thank you.
We now have some questions that we can start answering. So from Chris, question if you're taking them, what is needed to allow a car battery to charge back to the grid or a home when desired to allow the car to serve as grid storage?
It is already, it is already happening. As I shown in one of the diagrams, people are building bidirectional converters where they can charge the batteries, and also from the battery, they can connect it to the grid. So there are a lot of companies are working on that, and any new vehicles that are coming up, they have that feature already. So it is already going on.
Okay. From Ramanan Krishnamurti, are there life cycle analysis methods applied to these types of different engines and examine the total environmental and energy impact? And can you please share what the current thinking is on this?
The main thing, of course, in the electric vehicles, we don't have any engines, but electric motors and batteries, that is a major concern. So there is a lot of work people are analyzing what to do with that used batteries. Say the lifetime is say 10 years, or even if it is 12 years, what do you do with the batteries? And there will be a lot of waste, and that can cause environment problems. But the recent trend is to use those used batteries in the vehicles for grid integration as a battery energy storage system. Many of them are used. For example, Toyota, those nickel metal hydride batteries, Prius have a lot of nickel metal hydride batteries. So those batteries are being used for building the big energy storage systems for connecting to the grid. So that can last for some more time, but in the long term, as Ramanan questioned, there is a concern, as he pointed out. So that is to be still worked out. There is no particular solution for that at this time. Because the main thing is it has not been so much of a focus because there are not many electric vehicles. Only 1% or 1.5% of the total vehicles sold are electric vehicles. So it's still a long way to go.
Gotcha, it's still developing.
Yeah.
Stephanie has some questions. So the first one would be, if you were to buy a hybrid or an EV, which type would you choose? Like what make and model?
Yeah, I have a hybrid vehicle, but that is old. It depends on whether you need an SUV or a sedan. If you want to buy I would rather suggest people who want to buy plug-in hybrid vehicles. If you want to buy a hybrid vehicle, the reason is plug-in hybrid vehicles, you don't have to worry about the range. So you don't have to have two cars, one electric and one for long distance. So there are one I shown you, for example, if you are looking at SUV type of vehicle, that Outlander from Mitsubishi is a good one, 2020. And Ford Escape as a plug-in hybrid vehicle, that is available. And also Prius Prime is not an SUV, but Prius Prime is a good vehicle. And Chevy Volt is not available, but there are Audi as a vehicle. There are several companies, even BMW, of course, Stephanie needs BMW I think, that is also available as a plug-in hybrid vehicle. So, so there are a lot of options available. So I would rather suggest, if you are interested in hybrid, plug-in hybrid vehicle, so you don't have to worry for a range and all those things. And even if you don't charge it one day, you already have a gasoline. So even if you forget charging, you can still run with the gasoline engine.
All right, thank you. Another one is, what do you think is the best way to increase adoption of electric vehicles?
First thing is to reduce the price. And that is the one everybody is looking at. I think now I don't think that $7,000 credit is no longer available for, at least for Tesla, it is not available for many other companies may losing that. So the price is one important thing. And second one, as the battery improves, the range will go up. Then everybody will be going for electric vehicles. So the cost and the range, they are the two major concerns. If they are met, then I think it is very easy to commercialize the more electrical vehicles, or more the commercialization of electric vehicles will become simpler.
Yeah, definitely. Another question is from Ramiz Khan. They're asking, is it possible to get a BMS system?
What system? BMS, battery management system? What? I didn't follow.
Yeah.
Is it possible to get, means it is already there in the batteries. Every electrical vehicle battery pack has a battery management system already incorporated. They monitor the cells, each cell, and balance the charge equalization and the protection and the temperature. Everything is monitored. Their BMS systems are there already incorporated.
All right. And from
that is the question,
Danita,
I think so. Yeah.
Oh, yeah. From Danita, she asked, a lot of time in this presentation is talked about hybrids, but sales are really stalling. So are OEMs still investing in their development, or are they retreating?
Yeah, so hybrids are expensive, relatively more expensive than the electric vehicles. That is the reason that it is not being sold that much. So what is happening is there is a focus recently is on the electric vehicles, because battery is getting better and better. So people are buying more electric vehicles than the hybrid electric vehicles. For example, I mentioned the plug-in hybrid vehicles, but I would still say plug-in hybrid vehicle is only an intermediate. In 10 years from now, I feel there will be a lot more electric vehicles, and gradually plug-in hybrid vehicles, or even hybrid vehicles, first hybrid vehicles, then plug-in hybrid vehicles, they will all be fade away or go down. And it will be more and more electric vehicles. Because if somebody gets about, say, 400 miles range, and with a similar cost, or maybe slightly more expensive than a similar car, internal combustion engine based vehicle, I think people would prefer an electric vehicle than a plug-in hybrid vehicle.
All right. Danita's next question is actually, do many of the new electric vehicles come with the ability to use induction charging? And is it less efficient than plugging into a charger via a cord?
No, not many electric vehicles have the option of wireless charging. It is still being developed, because it is not that the vehicle manufacturers can incorporate that, but where you charge should have a facility. Your home should have that facility for wireless charging, because it has to go and park at a certain place, and it has to be aligned properly. There has to be on the other side of the secondary of the transformer, or the primary of the transformer, has to be in your garage somewhere, or wherever it is charged. So that's why it will take more time. And mostly this wireless charging will be used for fleet vehicles and also buses and that type of thing than individual vehicles. For example, in my garage, I may not do this type of a wireless charging facility.
Yeah. So from Samal, they just read about EV's battery explosion causing fires on the road. How safe are the EV batteries in reality?
EV batteries are much safer than the internal combustion engine vehicles. EV batteries are packed very well, because internal combustion engine, of course, if something happens, how many cars have caught fire because of the gasoline engine? The temperature is also quite high, internal one, but it has to be packed, and also they are all tested very well. But in some cases, it can happen. It is not because of the crash or anything, because the lithium-ion battery has some, because of the liquid electrolyte, it has some problems, but most of the problems are being taken care of. Because, see, in the early stages, you always have some problems. So, but over a long run, I think battery is not a problem at all.
All
And
right.
actually, in many of the cars, you are sitting on the battery. The battery is just below your seat where you are sitting. So that is where it is mounted, or it is next to you. Between the passenger seat and the driver seat, the batteries are there in long. For example, in GM vehicles, many of them, they have like that. Yeah. So it is particularly safe.
Oh, awesome. That's good to know. Another question from Arnur is, what is the present and future of fuel cell cars? What are their challenges?
Yeah, fuel cell car, the challenge is the infrastructure. So fuel cell cars, people have been working, or companies are working for a long time on fuel cell cars. For example, there is a company called Ballard. They started for the fuel cell vehicles, but there are not many fuel cell vehicles. That is the problem. Why there are not many fuel cell vehicles? Because there is no charging infrastructure. Why there is no charging infrastructure? Because there are no fuel cell vehicles. So in California, there are a lot of facilities where you can fill in the hydrogen for the fuel cells, and also Department of Energy is putting a lot of effort to install the charging or the filling stations, hydrogen filling stations. So the main thing for not having fuel cell vehicles are the filling up of the gasoline. And other one is, of course, they're expensive when compared to even the hybrid vehicles.
Okay. From John, he says he currently has a plug-in hybrid, but his next car will be purely electric. Do you agree that the U.S. must accelerate the installation of DC fast chargers across our country to get more people to accept pure EVs?
I perfectly agree. I have a hybrid vehicle. My next vehicle will be electric vehicle. So I think there should be supercharging stations or fast charging stations. More and more have to be installed. That would help. For example, there are chargers that can charge in 15%, or if in 15 minutes you can charge up to 80% state of the charge. So there are chargers, but there are more and more have to be installed. Okay. I fully agree with what said.
Yeah, that's a good statement. From Chris, don't you think infrastructure is critical? Like battery?
Infrastructure critical for the electric vehicles?
Yes.
Yes, electric vehicles, the infrastructure is very important where you can charge, because every time if you're driving a particular long distance, you cannot come home and charge and go back. You have to charge at different places, like we fill in the gasoline for the gasoline vehicle. The infrastructure is very critical, and we need to install more supercharging stations. And also another thing, we should be able to charge the batteries using renewable energy system, renewable energy based on wind or solar. That will further accelerate the sale of electric vehicles, because people are more conscious. Okay, my electric vehicle is not emitting any emissions or carbon dioxide by using this renewable energy. So yeah, infrastructure is very critical. If all the electric vehicles are charged by the renewable energy systems, then we don't need for regular car a fuel cell vehicle also, because anyway there is a renewable energy, you can charge the batteries and then go for long distance. The advantage of fuel cell vehicle is as long as there is a hydrogen in the vehicle, you can go for long distances, and also it has lower emissions.
Definitely, having it attached to the renewable resources would be amazing.
Yeah.
From Maxence, he asks, why are power electronics needed to resist up to 250 Cs? It seems very high. Yeah,
the reason is the temperature of the power converters will go up. If they can take 250 degrees Celsius, because when we can reduce the size of the power electronics, and we can reduce the size of the heat sink that cools the system. Our cooling, now we cool using the liquid cool. They're all 50%, most of them, they use 50% ethylene and water, glycol, ethylene glycol and water, 50-50. So we don't need that liquid cooling. We can use maybe air cooling, or we can still use the liquid cooling, but we can reduce the size of the overall power converter, because our ultimate aim in electric vehicles is to reduce the weight of the system. So we used to say when we were working on EV1, if you reduce it by 1 kilogram, I think you can go another 3 kilometers extra, something like that. So you can your driving range increases because you want to use the energy for driving you rather than driving all the extra unnecessary weight in the system.
Yeah. Another question is from Yusuf. They're asking, now that Joe Biden is in office, do you expect that production of electric vehicles will be accelerated?
I hope so. I think so. That's what, because there is a more emphasis on the renewable energy. And also, I think we are getting back into Paris Agreement, the climate agreement, and all those things that definitely will help in selling more electric vehicles.
All right. Well, I think we're running out of time. It's already 2 o'clock, but I would like to say a big thank you to Dr. Rajashekara for having such a wonderful presentation. Again, our partner, Evolve Houston, and for everyone in the audience. It was really amazing to have you and hear all your questions. Don't forget to please join us on February 12th for the electrification of rail and sea transportation by Dr. Krishnamurthy.
Thank you.
Hope to see you all again.